Okay, so we've looked at the quick union and quick find algorithms, both of which are easy to implement, but simply can't support huge dynamic commutativity problems. So how are we going to do better? That's what we'll look at next. A very effective improvement is called weighting, and it might have occurred to you while we were looking at these algorithms. The idea is to, when implementing the quick union algorithm, take steps to avoid having tall trees. If you've got a large tree and a small tree to combine together, what you want to try to do is avoid putting the large tree lower. That's going to lead to long, tall trees. And there's a relatively easy way to do that. What we'll do is we'll keep track of the number of objects in each tree. And then we'll maintain balance by always making sure that we link the root of the smaller tree to the root of the larger tree. So we avoid this first situation here where we put the larger tree lower. In the weighted algorithm, we always put the smaller tree lower. Let's see how we implement that. Let's see a demo first. Okay, so again, we start out in our normal starting position where everybody's in their own tree. When there's only 2 items to link, it works the same way as before. But now when we have 8 to merge with 4 and 3, we put the 8 as the child, no matter which order the arguments came, because it's the smaller tree. So 6 and 5 doesn't matter, whichever one goes down doesn't matter. 9 and 4. So now 9's the small one, 4's the big one, so 9's going to be the one that goes down below. 2 and 1. 5 and 0. So now 5 and 0, 5's in the bigger tree, so 0 goes below. 7 and 2. 2's in the bigger tree, so 7 goes below. 6 and 1. They're in equal sized trees. And 7 and 3. 3's in the smaller tree, so it goes below. So the weighted algorithm always makes sure that the smaller tree goes below. And again, we wind up with a single tree representing all the objects, but this time we have some guarantee that no item is too far from the root, and we'll talk about that explicitly in a second. So here's an example that shows the effect of doing the weighted quick union, where we always put the smaller tree down below for the same set of union commands. This is with 100 sites and 88 union operations. You can see in the top, the big tree has some trees, some nodes, a fair distance from the root. In the bottom, for the weighted algorithm, all the nodes are within distance 4 from the root. The average distance to the root is much, much lower. Let's look at the Java implementation, and then we'll look in more detail at that quantitative information. So we use the same data structure, except now we need an extra array that for each item gives the number of objects in the tree rooted at that item that we'll maintain in the union operation. Find implementation is identical to for quick union. You're just checking whether the roots are equal. For the union implementation, we're going to modify the code to check the sizes and link the root of the smaller tree to the root of the larger tree in each case. And then after changing the ID link, we also change the size array. If we make I a child of j, then we have to increment the size of j's tree by the size of i's tree. Or if we do the other way around, then we have to increment the size of i's tree by the size of j's tree. So that's the full code in white for implementing quick union. So not very much code, but much, much better performance. In fact, we can analyze the running time mathematically and show that the find operation, it takes time proportional to how far down the trees are in the node, the nodes are in the tree, but we can show that it's guaranteed that the depth of any node in the tree is at most the logarithm to the base 2 of n. We use the notation LG always for logarithm to the base 2. And so for if n is 1,000, that's going to be 10. If n is 1,000,000, that's 20. If n is 1 billion, that's 30. It's a very small number compared to n. So let's look at the proof of that. We do some mathematical proofs in this course when they're critical, such as this one. And why is it true that the depth of any node x is at most log base 2 of n? Well, the key to understanding that is to take a look at exactly when does the depth of any node increase. When does it go down further in the tree? Well, the x's depth will increase by 1 when its tree, T1 in this diagram, is merged into some other tree, T2 in this diagram. Well, at that point, we said we'd only do that if the size of T2 was bigger than or equal to the size of T1. So when the depth of x increases, the size of its tree at least doubles. So that's the key, because that means that the size of the tree containing x can double at most log n times, because if you start with 1 and double log n times, you get n, and there's only n nodes in the tree. So that's a sketch of a proof that the depth of any node x is at most log base 2 of n, and that has profound impact on the performance of this algorithm. Now, instead of the initialization always takes time proportional to n, but now both the union and the connected or find operation takes time proportional to log base 2 of n. And that is an algorithm that scales. If n grows from 1,000,000 to 1 billion, that cost goes from 20 to 30, which is quite acceptable. Now, this was very easy to implement, and we could stop, but usually what happens in the design of algorithms is now that we understand what it is that gains performance, we take a look and see, well, could we improve it even further? And in this case, it's very easy to improve it much more. And that's the idea of path compression. And this idea is that, well, when we're trying to find the root of the tree containing a given node, we're touching all the nodes on the path from that node to the root. While we're doing that, we might as well make each one of those just point to the root. There's no reason not to. So when we're trying to find the root of p, after we find it, we might as well just go back and make every node on that path just point to the root. That's going to be a constant extra cost. We went up the path once to find the root. Now we'll go up again to just flatten the tree out. And the reason would be no reason not to do that. We had one line of code to flatten the tree amazingly. Actually, to make a one line of code, we use a simple variant where we make every other node in the path point to its grandparent on the way up the tree. That's not quite as good as totally flattening. Actually, in practice, it actually is just about as good. So with one line of code, we can keep the trees almost completely flat. Now, this algorithm people discovered rather early on after figuring out the weighting, and it turns out to be fascinating to analyze, quite beyond our scope, but mention this example to illustrate how even a simple algorithm can have interesting and complex analysis. And what was proved by Hopcroft and Ullman and Tarjan was that if you have n objects, any sequence of m union and find operations will touch the array at most a constant of n plus m log star n times. Now log star n is kind of a funny function. It's the number of times you have to take the log of n to get 1. It's called the iterated log function. And in the real world, it's best to think of that as a number less than 5. Because log star of 2 to the 65536 power is 5. So that means that the running time of weighted quick union with path compression is going to be linear in the real world, and actually can be improved to even a more interesting function called the Ackermann function, which is even more slowly growing than log star. And another point about this is it seems this is so close to being linear, that is time proportional to n, instead of time proportional to n times a slowly growing function in n. Is there a simple algorithm that is linear? And people look for a long time for that, and actually it works out to be the case that we can prove that there is no such algorithm. So there's a lot of theory that goes behind the algorithms that we use, and it's important for us to know that theory, and that'll help us decide how to choose which algorithms we're going to use in practice and where to concentrate our effort in trying to find better algorithms. It's an amazing fact that was eventually proved by Fredman and Sachs that there is no linear time algorithm for the union find problem. But weighted quick reunion with path compression in practice is close enough that it's going to enable the solution of huge problems. So that's our summary for algorithms for solving the dynamic connectivity problem. With using weighted quick union and with path compression, we can solve problems that could not otherwise be addressed. For example, if you have a billion operations on a billion objects, I said before it might take 30 years. We can do it in 6 seconds. And what's most important to recognize about this is that it's the algorithm design that enables the solution of the problem. Faster computer wouldn't help much. You could spend millions on a supercomputer and maybe you could get it done in 6 years instead of 30 or in 2 months. But with a fast algorithm, you can do it in seconds on your own PC.